Here we'll do a problem where we first need to do a substitution. I made it pretty simple in this case. And then we're going to do partial fractions, and it's going to be one twist that we didn't see in some of the previous examples. So here's our integral. And what we notice is that there's e to the x's everywhere. In fact, x never appears except as e to the x or e to the 2x. And of course, e to the 2x is just e to the x quantity squared. So that doesn't necessarily mean substitution is going to work until we try it. But if we try u equals e to the x, then the first thing we would look at is, well, what's du? That's e to the x dx. Aha! This top up here, as I pointed out, that's e to the x, let's say, times e to the x. Okay, so the e to the x dx is going to split off to be a du, and then everything else will turn into u's. So this is going to be integral 10u, and then the e to the x dx is a du. And then the bottom we've got u plus 2, and we've got u squared, observing again that e to the 2x is just e to the x quantity squared, plus 2u plus 5. All right, so now remember to check, is the degree of the numerator less than or strictly less than the degree of the denominator? It is, so we don't have to do long division. Let's just bring that down so I'm not always getting in the way of that. Okay, well actually, what we should really look at right now is just the algebra. What's that going to be? Well, so I have a linear factor, and then notice I could try to factor this factor, but it really won't do. It really won't factor. And one way to tell for sure that it's not going to factor is to look at the discriminant of that. B squared minus 4ac is 4 minus 20 minus 16. That's less than 0. The roots of this quadratic are complex. They're not real, so it's not going to factor into linear factors. And that's just a fact that some quadratics can't be factored in the real numbers. We're choosing not to use complex numbers here. You could. And so we just don't actually factor that. So this is called an irreducible quadratic. And so now, no matter how good you are at factoring polynomials, that can be a chore in itself, we need to figure out what that does. So the pieces we've got are going to be this very ordinary, so by now, linear factor. And then we're going to have something where the denominator is just plain u squared plus 2u plus 5. Once again, a little bit like the repeated linear factor, we're going to get something a little more complicated here. It turns out if I just put an a here and a b here, that's not going to be enough to match an arbitrary numerator over here. If you think about what would happen, for example, if I had bu plus c, if I do common denominator on this kind of expression, you will totally get something over here, exactly of this form, with some numerator. And so there's no reason to expect that I shouldn't need the bu plus c over here. This is basically the most complicated proper rational function with this denominator, not just a number over this denominator, which wouldn't be the most general case. Okay, so I'm not going into too much more depth about the algebra of why you need that. Then just clear the denominators. Excuse me. Okay. And plus quantity bu plus c, careful, there's an implied quantity there, and then times u plus 2. Okay, let me just delete that so it's not in our way. All right, so now we can plug in. Unfortunately here, with the irreducible quadratic, it does not give us nice values to plug in. Again, since we're not going to complex numbers, we can definitely plug in u equals minus 2. That's one of the roots of the original polynomial here. It's showing up as a factor here, and that will help. That will in fact give us a. We're going to get minus 20 equals a times, and I'm going to plug that in carefully, 4 minus 4 plus 5, and so that's nice. So a is going to be 5a is minus 20, a is minus 4. Okay, great. That's at least some progress. Now I'm going to plug that in. And the trouble is there's no there's no real value of u that's going to make this 0. That's what it means. One of the things it means to be an irreducible quadratic. We check that the roots are not real. And so we can't use this plug-in strategy anymore, but we can always go back to the equate coefficient strategy. This is where that is pretty much, you have to do it, even if you've got some other clever things up your sleeve. So I'm just going to go ahead and distribute that, start expanding this out. Excuse me. And then won't do it in place. Let's just copy this. And then that's going to be bu squared plus cu plus 2bu plus 2c. And let me just rewrite the 10u. And now let's collect. Excuse me. Okay, and then the linear terms are 2bu minus 8. That's right, 2b minus 8 all times u. And then the, just 2b plus c. There we go, that's important. And then plus 2c minus 20. Let's see. So we've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And you got to be careful with the signs, but it's looking good. Okay, so now we can equate coefficients. There is no quadratic coefficient over on the left. Oops. And so that is nice. It's saying b0 equals b minus 4. Hey, good. We got b equals 4. We're good on that. Okay. The linear coefficient, interestingly enough, only involves c. Notice that makes sense because the b had the u attached to it. And so that's never going to contribute to a linear coefficient. And we're getting 0. That's the constant coefficient over here. And that's equal to 2c minus 20. This isn't really too bad. 2c equals 20. C equals 10. Okay. And then we can just do this as a double check. Remember, if you've done the plug-in strategy, the equate coefficient strategy is really, that can give you all the coefficients completely. And if you've already done a plug-in, then it just means there's some value to this as a double check. Let's do it. 2b plus c minus 8. We are claiming that's 8 plus 10 minus 8. Okay. Oops, sorry, minus 8. That's equal to, 10. And that's what it should be, because it should be the linear coefficient over here. Okay, so that's an independent check. Groovy. Okay, so now we have our coefficients. Minus 4, 4, and 10. We're going to go back up to here. Minus 4, 4, and 10. Excuse me. Okay, and now let's just rewrite the fact that we really wanted the integral on both sides. Du. So that's going to be the integral of this du plus the integral of this du. And most likely we're going to need to use different methods on those. We're going to just split them up. And indeed, this one's pretty familiar by now. Minus 4 times ln of u plus 2. It's the natural log. Now, how do we do this? Okay, well, there's a few ways to, a few different details in the way to attack it. But the main thing is this is a quadratic on the bottom. We really want to complete the square on that because we want to be able to do a sub to get this to not be a problem. So we're going to complete the square. Let me just set it up to have a place for this. Okay, u plus something squared plus some coefficient, and that's going to change that 5. Now I've set it up to be fairly simple. You might want to review completing the square at this point, but the main thing is you take half of that 2. It's going to be u plus 1 squared. If it were just u plus 1 squared and nothing else, that would be u squared, check, plus 2u, check, plus 1. Oh, we need it to be plus 5, so there's an extra 4. Sometimes you have to do a little bit more thinking, do it a little more carefully, but I set it up so that it was not too bad. You know what? And I'm going to write that as a 2 squared because that makes it set up for a trigonometric substitution. Okay, so let's do that. So this is all good. We're done with that. Okay, so now the trig sub is going to be, Let me get that back. That's going to be u plus 1 equals 2 tan theta. When you have something squared plus something squared, that's going to be a tan substitution. If you can write it as the variable part squared, keep thinking I'm right-clicking there, plus something else squared, that coefficient's going to be here. Let's check that this all makes sense. du is then going to be 2 secant squared theta. Okay, and I like to just really carefully write out that quadratic, I don't think I need parentheses there, to make sure that it's really working. The quantity u plus 1 squared plus 2 squared is 2 tan theta all squared plus 2 squared. That has a common factor of 4 times the key 1 plus tan squared theta, and that's 4 secant squared theta. Okay. And I forgot a d theta here. Okay, so we're good, and a nice thing is that the du is going to cancel the secant squared. Now, the thing is, 4u plus 10, that is, that's something we also have to convert. Okay, so u is 2 tan theta minus 1. So 4u plus 10 is going to be 8 tan theta minus 4 plus 10, so plus 6. Whew, that's a lot of stuff to plug in, but we'll get it. So let's just actually, let me just copy off this separately. We'll put it all together at the end. Okay, so we've now got, that's the integral of 8 tan theta plus 6 over 4 secant squared theta times 2 secant squared theta. So that's, as I pointed out, that's a nice cancellation. D theta. Okay, so it's all set. And now we get some nice cancellations. The secant squared is the big one. There's a 2 that cancels. Actually, 2 2's cancel. That cancels down to a 3, actually. So the entire denominator goes away. So 4 tan theta plus 3 d theta. That's it. Okay. Not too bad. Excuse me. So we have to remember what the integral of tan is, and that's, excuse me, the log, that's minus log cosine. That's one way to write it. Plus, well, integral of 3 d theta is just 3 theta. Okay, I'm going to put the plus c in at the very end. Now we have to start converting back. Well, we have to convert this back to u, and then eventually we're going to convert back to e to the x. Okay, so minus 4 log of, well, cosine theta. Let's see. If u plus 1 is 2 tan theta, we have to make sure we get that. So another way to say that is u plus 1 over 2 is tan theta. I'm not going to draw the triangle, but that's not a bad thing to draw in this case. And cosine theta is going to be 2 over the square root of, and not surprisingly, we're going to see the quadratic we started with come in. This is u plus 1 squared plus 2 squared, which is just u squared plus 2u plus 5. Okay, so there we go. Okay, so that, whoops, Control C, Control V here. Okay, whew, this is getting intense. Theta, what is theta? Put that in here. Theta, of course, is the inverse tangent of u plus 1 over 2. And so that's going to go here. This is pretty involved. Okay, finally, we can combine that. Actually, let me just bring down the whole thing. There's what we're calculating, although that's in the U language. Equals, now we had a little bit, it wasn't too bad. That's this thing. Just assembling the pieces. Plus, put it on a new line. Plus all this stuff. Might as well put in a plus C here. Okay, so actually minus. Okay. Plus c. All right, now we still haven't converted back. But one thing I really should do here, this is an unnecessarily complicated thing. We've got the log of something with a square root here. We've also got a 2 inside a log. There's various ways we can simplify this, and we really should, especially if we're going to compare this like to the back of the book where they tend to do some simplifications. So that's going to be minus 4 times the log of 2 minus the log of u squared plus 2u plus 5 to the 1/2. Well, you know what? That comes out as a 1/2 here, using one of our rules of logs. And then plus all this stuff. And then here's something that often happens. The minus 4 log 2 can be just absorbed into the arbitrary constant by just changing what we mean by the constant. And so it's kind of weird sometimes to people that can just go away. Okay, a minus 4 times a minus 2 turns into a plus 2. And that's really substantially simpler. That is definitely worth doing that simplification. If you're wondering, ooh, wait, the absolute values went away. Remember, one of the facts about this being an irreducible quadratic, this thing is always positive. So you don't actually need the absolute values there. Okay, finally, we put back the fact that u was just code for e to the x. It's a pretty long one, isn't it? I was sort of dreading doing one of the examples where we really do a lot of stuff because I knew the video was going to be long. Maybe I should have made it 2 parts, but too late now. You can definitely take a popcorn break. I hope you took a popcorn break in the middle. And finally, we're done.